In Chapter 14, we discussed the cardinality of sets. So we're going to start off with talking about sets with equal cardinalities. So what does it mean for two sets to have the same cardinality? We've thought of this before, right? Maybe I have a set A, and its cardinality is 5, and I have another set B. Its cardinality is also 5. So I can think about A as a set that's got 5 different elements in it. And I can think of set B as another set that also has 5 elements. Right, and that's fine. They both have cardinality 5, so that means they have the same cardinality. But that idea of actually assigning a number to the cardinality, that's not going to work if we move into infinite sets. So we want to be able to think about infinite sets now, and how we can think about these infinite sets having the same cardinalities or different cardinalities. So we're going to be able to talk about different sizes of infinity. So we want to be able to change our sort of point of view a little bit and consider these sets as having the same cardinality or the same size without actually referring to that size. So one thing I can do is I can say if they have the same size, then there's some nice way to match the elements in one set to the elements in the other set. In a way where every element in the first set gets mapped to exactly one element in the second set, and I don't leave anything behind. Right? Well, that's exactly the same as saying there is a function, f, from the first set to the second, and that function is 1 to 1, so that two elements don't get mapped to the same element, and onto. So there is a bijective function, f from a to b. And when we talked about bijective functions, we said if you have finite sets, you can only have a bijective function if the cardinalities of those sets are the same. And now we're going to sort of turn that around and say we're going to define the cardinalities of two sets to be the same if there is a bijective function f between those two sets. So let's go ahead and talk about that some more. Okay, so this is my formal definition here. We say two sets, A and B, have the same cardinality if there's a bijective function f from A to B. So it has to be bijective. That's the big important thing here. And if it is impossible to find a bijection between those two sets, we say that their cardinalities are not equal. Right? So we have unequal cardinalities if there's no such bijective function. So either there is a bijection, in which case they have the same cardinality, or there is impossible to have a bijection, in which case they don't have the same cardinality. So let's go ahead and look at some examples of that. The first thing we're going to show is that the cardinality of the natural numbers is the same as the cardinality of the integers, which seems kind of surprising, right? If I think about these natural numbers here, I've got just 1, 2, 3, all the way up to infinity. And then my integers, they're also going to have 1, 2, 3, all the way up to infinity, but also -1, -2, -3, down to negative infinity, and 0. So it looks like there's more than twice as many integers, but in fact, we can define a bijection between these two sets. Therefore, those sets actually have equal cardinalities. So how do I actually define this? So let's say I'm trying to define a function from the natural numbers to the integers. I need to make sure that I hit every single one of my integers. So I'm going to think about having sort of my natural numbers 1, 2, 3, 4, 5, 6, and so forth. And then I'll have my integers 0, 1, 2, but also -1, -2, -3, and so forth. So if I started out my function by just having each of these integers go to itself, that's not going to be bijective because I'm going to leave off all of my negative ones. So instead, what we can do is maybe we take 1 and just send that to 0. That's kind of the odd man out. We want to make sure we kept that covered. And then I can send 2 to 1, and then 4 to 2. So I'm just going to sort of skip my numbers here. And that way I can send 3 to -1, 5 to -2, and then let's see, if I keep going, 7, 8, 9. 7 gets sent to -3. 8 will go to 4. 9 will go to -4, and so forth. So we can actually define what this function is using a piecewise function. So I could say that my f of n is going to be 0 when n is 1. For the even ones, 2, 4, 6, 8, they just got sent to n over 2 when n is even. And then when it was odd, 3 got sent to -1, 5 got sent to -2. So if I subtract 1 and then divide by 2, and then I'd make that negative, I think that'll be the right thing. So let's just check. 9, for example, 9 minus 1 is 8, divided by 2 is 4, and then I make it negative. So that's going to be what happens when n is odd and not equal to. Oh no, that's right. I was going to say not equal to 1, but it wasn't that. I should have said here it's even and not 1. Wait, what? I'm so confused. Down here, n is not equal to 1. Perfect. All right. Oh, I guess if n equals 1, that still would give me 0. So that works out as well. Very good. So I can actually leave off that case. Nice. So that's going to be my function. And we can sort of see from this picture that this is going to be one-to-one and onto. I'll leave that as an exercise for you to show that this Fn is bijective. And you'll see that in your problem set. So you need to show that it's one-to-one or injective and that it's onto or surjective. So it does seem a little strange. It does seem like there's more integers than there are natural numbers. But because we can define this bijection, we can actually match them all up in a way that we get everyone matched uniquely. So these sets do have the same cardinality. Okay, so now let's look at two other infinite sets, R and N, and I want to determine if these two have the same cardinality. So if they have the same cardinality, so if the cardinality of R is equal to the cardinality of N, then there exists some bijective function, f. I'm going to say it goes from N to R. It can go either way. So I have that bijection if they have the same cardinality. So assume that exists. So then assuming it exists, I can think about what f of 1 is, and f of 2 is, and f of 3 is, and so forth. So I can actually list out all of my real numbers in order. So I can list all real numbers in order. And by not the regular order that we're used to, but an order defined by this bijection. So whatever 1 gets mapped to, whatever 2 gets mapped to, whatever 3 gets mapped to. So over to the left here in this chart, I've got an example of what one of those functions might look like. So maybe in this magical bijection, 1 gets mapped to this number 0.4, which has a whole bunch of zeros after it. And then 2, maybe that one was 8.5, blah, blah, blah. Right? So a real number just is going to have some possibly infinite decimal expansion. So I'm just going to list out all of my different real numbers that correspond to this bijection that exists if they were equal cardinalities. So if I make this infinitely long list, I should have every single real number. So every single real number should be listed here. And what we're going to do is we're going to show that we get a contradiction. we're going to show that it is impossible that every single real number can be listed, because we can use this list to create a real number that's not in our list. So let me write that out. We're going to use this list to create a real number not in the list. So how do I do that? I'm going to go along the diagonal here. So I'm going to take the first decimal point from my first number, the second decimal point from my second number, the third decimal point from my third number, and so forth. So I'm just going to list those out. This is not the number I'm creating. This is a different number. But I'm just going to list out those decimal places along that diagonal. And then I'm going to follow this pattern to create a new number. If the digit is not a 0, we're going to put a 0. So I get zeros for every one of these digits that wasn't a 0. And if it is a 0, we're going to put a 1. So I put a 1 for every single one of those zeros. And I continue doing this infinitely long. And my claim is this new number I created is not in the list. So how do I know for sure that that new number is not in the list? It's because it's different from the nth number at the nth digit. Right? It can't be the first number because its first digit is different than that first number because that had a 4. It can't be a second because its second digit is different. It can't be the third because its third digit is different than the third. Its fourth digit is different than the fourth. Its fifth digit is different than the fifth. So even if it was the 1 millionth number, well, it can't be the 1 millionth number because it would be different in the 1 millionth digit because we change the digit for every single one of those numbers. So it would be impossible to have this bijection because if we did have a bijection, we could list out all the real numbers, but this list can't possibly contain all the real numbers because I can always create a new real number that it isn't contained in there. Therefore, we get that the cardinality of the real numbers is not equal to the cardinality of the natural numbers. If you want to read more about this, this is called Cantor's diagonalization argument. So I encourage you to read some more about that if you're interested. It's how we show that there are more. Right now we're just showing the different sizes, but we'll see soon that there's actually more real numbers than natural numbers, even though there's the same number of integers as natural numbers. So take a couple minutes to think through that, and we'll talk through that a bit more in class. Okay, for our final exercise in this section, I want you to think about showing that the cardinality of the real numbers is the same as the cardinality of the interval 0, 1 on the real line. So if I just think about this open interval, not including 0 and 1, here, the number of numbers, right, the cardinality of that set is equal to the cardinality of the entire real line. So I'm just going to draw those as separate axes. So remember, to show that two sets have the same cardinality, you need to find a bijective function from one to the other. So you're looking for a bijection between those two sets to show that they have the same cardinality.